Well, thank you everybody for coming to today's condensed matter seminar. It's my great pleasure to have Professor Andrew Lucas from University of Colorado Boulder being our speaker today. So Andrew did PhD at Harvard University working with Professor Shubir Sachdev, and then he went to Stanford to do to take on more foundation postdoc fellowship and there. And then recently, I think it's in 2019, right?
Right.
Andrew joined Colorado as an assistant professor. And I think last year he got a very prestigious prize. That's a Sloan Fellowship last year. Congratulations. I actually, this is also my first time seeing Andrew in person remotely, but I got to know his work through through our own research on interacting two-dimensional electrons in 2D semiconductor quantum well. So we were interested in the possible viscous transport of interacting 2D electron system behaving similar to like the fluids. Okay, as we know, like in Fermi liquid picture of electrons in metal. So we say Fermi liquid, but actually electrons can be viewed as independent quasi-particles. So they do not really move like a conventional or classical fluid. But more recently, in the last several years, there has been a lot of progress in in hydrodynamic behavior of electrons in unconventional materials like graphene, and then so we got interested in those work, and then we saw Andrew's nice work on theoretical studies of hydrodynamics of electrons. So then I invited him to give a talk here. I think it's better to hear Andrew talking about this topic. So I will give the stage to Andrew.
All right. So yeah, thank you very much for the invitation to speak here today. Happy to be here, albeit remotely. So today I'm going to sort of overview two sort of particular topics and in this now sort of rather broad field of electron hydrodynamics. I think these two subjects are sort of particularly interesting and maybe sort of represent more of where this field can be going over the next couple of years. Let me begin by acknowledging my funding and collaborators. So the first part of the talk after the introduction will be on some experimental work done with the group of Anya Jayek at UCSB together with Andrea Young and Anya's students, Alec and Simon, I think did a lot of the work on the experimental side. And then towards the end of the talk, I'll discuss some theoretical work done with a graduate student at Stanford, Caleb Cook, who's kind of a unofficial group member of mine. Okay, so let me begin by sort of introducing a little bit about how people like me and my PhD advisor got interested in this subject of electron hydrodynamics in the first place. So, back in 2014 and 2015, we were and still are interested in understanding sort of strongly correlated electrons and their dynamics and transport in various exotic quantum materials. So here's one example that this kind of chemical compound that I won't try to rattle off to you, but this is it's a high temperature superconductor. And so what is this colorful plot? It's a plot of resistivity in some sense as a function of temperature and then this chemical doping X. So there's the superconductivity at low temperature. At low doping, there's the spin density wave order, but this kind of rainbow of different colors is coming from the scaling of the resistivity of this metal with respect to temperature. So we're basically asking, do we see, for example, rho scaling like t squared or t to the fifth or t linear, what's going on. So in this blue part of the picture, we have rho scaling like t squared. And we believe that this is kind of a conventional Fermi liquid metal. So we've got well-defined electronic quasi-particle excitations. It's kind of it's not too strange. But then, as we move into this orange fan, kind of right here, we see that we find robust T linear resistivity. And this is sometimes called Planckian resistivity. It's got a very sort of mysterious prefactor that has some amount of universality. And these were the kinds of puzzles that we were thinking about. In particular, if we think about this T linear resistivity, this kind of pattern, this phase diagram, at least quote unquote phase diagram of resistivity, shows up in lots of different materials, even when the microscopics appear quite different. I mean, maybe we don't have spin density waves in some materials, but they exist in other ones, like here. And so there was, and still is, some hope that maybe there's some universal language to talk about strongly correlated electrons and their transport behavior, in these so-called non-Fermi liquid or strange metal regimes, like in this material. And so maybe just I'll say a couple words about why these are sort of particularly difficult problems for conventional methods, or sort of what are we really getting at when we look at these transport phenomena. So, if we go to our textbook and we look up the Drude formula for resistivity, right? So we find that the resistivity is going to be some effective quasi-particle mass divided by a density times E squared, the charge on the electron. And these are all what I would say are thermodynamic kind of quantities. These we sort of understand, and often we can compute them reasonably from first principles, or certainly measure them if we can't compute. And then there's this residual kind of lump everything together factor of 1 over tau, where tau is interpreted as some sort of a scattering in time. Okay. And so the difference between this t squared versus t, for example, is going to be coming from this scattering rate. Okay. The t squared is going to be our sort of classic t squared scattering rate for electrons on a Fermi surface, just coming from kinematic considerations. And so this mystery of the T linear resistivity is ultimately a question about dynamical behavior of some strongly correlated electron soup. And this is a very difficult problem because we're doing many body quantum mechanics. We don't necessarily have well-defined quasi-particle excitations. So we can't sort of, at least systematically, write down a Boltzmann equation to try and solve for the dynamics in such a system. And so we were sort of thinking, are there any other perspectives that one might have on this sort of strongly correlated quantum soup of electrons? How will it behave at finite temperature? Is there some simple language that we can use to talk about such a system? And the sort of key observation or insight that I think many groups sort of began to have, sort of really picking up around 6 to 7 years ago, was that a lot of the story that I just told, that we have this very strongly correlated soup, and it's sort of microscopically intractable, but maybe there's some macroscopic universality that arises. This, at least superficially, has some similarity to an old classical story, that was understood 100 years ago. So imagine that you're trying to understand, how to fly an airplane, or how to build an airplane that won't fall out of the sky. And this is a very difficult problem. If you imagine, right, the air has huge numbers of molecules, 10 to the 27, 10 to the 28, right? These are horrific numbers. Even today, you're not going to solve for that many equations on a computer. But nevertheless, right, airplanes fly, and we simulate their performance, in numerics. So how is it possible that we're able to do that, given that this 2 is a complicated, chaotic, microscopic system at short scales. And we've got 10 to the 28 interacting particles. How is it that we nevertheless can simulate, airplanes? And the reason, right, is that we don't simulate the dynamics of all of these different molecules. That would be far too complicated. Instead, the argument that we make is as follows. So let's imagine that we take some cell of air, some cell of this gas. Maybe it has a characteristic length scale I'll call capital L. And if capital L is very large compared to a mean free path, which maybe I'll schematically denote here as the typical distance between these little blue balls. If L, capital L, is very large compared to my mean free path, okay, then I can think of this whole cell as being in approximately at least local thermal equilibrium with itself, okay? So I have so many particles and they're chaotic, they have chaotic dynamics. So I expect that, by the postulates of statistical mechanics, that this sort of local fluid cell will come to equilibrium. And once that happens, right, I can characterize this fluid cell by a small number of parameters like pressure or velocity. And then all I need to do is I need to understand how the sort of macroscopic fluid cells in my picture, interact with each other. So how does pressure, move from one fluid cell to the next? And how does velocity move, and so on, okay? And that's the theory of hydrodynamics. Now, what's remarkable about hydrodynamics is it's remarkably insensitive to microscopic details, okay? As I'll argue for a simple example in a minute, we really need to know very, very little about what's going on microscopically. And even when the microscopic equations like in water are very, very complicated, I think even today it's not a trivial problem to, say, calculate viscosity of water from first principles. Even though we can't do that, right, we still can make extremely quantitative predictions about the flow of water because we have these hydrodynamic equations that essentially coarse grain out all of that microscopic complexity. So let's try to understand a little bit about how this story would have worked, and then we can ask, if it makes sense to talk about this in the context of electrons. Okay, actually, in the context of electrons, we already do sort of take a hydrodynamic perspective. We don't often say this word hydrodynamics in this context, but here's a story that has a very similar flavor to the one I just said about gases and airplanes, but this story is of course in a solid state context. So let's imagine that we have a metal here, and this metal has maybe lots of impurities that I'll schematically denote like this. And at low temperatures, the resistivity of this metal will be dominated by single electrons sort of bouncing off of these impurities. And so let's just imagine, I've got this ensemble of electrons, they're bouncing around between different impurities. And I don't really want to keep track of every electron in the system, right? That's a very complicated thing to do. And in some sense, the single particle trajectories, even if I sort of imagine that there's no interactions between electrons, but the single particle trajectories here could be very chaotic, right? They're moving in this disordered landscape. The nature of the impurities might lead to complicated scattering. And I don't want to keep track of any of that. Instead, what I want to do is say, for each electron, right, or if I look at a big region of space, okay, the electrons aren't being simultaneously created or destroyed, right? They can only sort of flow in or out of a given region. So I have number of electrons is conserved. And I also know, right, that this dynamics is local. So kind of these two bits of information are already enough to build up my effective description of the long wavelength behavior of this system. So Okay, locality of this dynamics tells me that if I look at the rate of change of the number density of electrons in a given cell of space, that is going to be equal to minus the divergence of some electronic current. Okay, and I'll often just use some index notation in this talk because once we start talking about viscosity, we'll have objects with lots of indices, and this is just a better notation. Okay, but this is just the continuity equation for charge. It's nothing fancy. Okay. And the only problem with this equation is that it's underdetermined, right? I don't know what the current is as a function of the density. So hydrodynamics is basically the postulate that we can write down a local expression for current in terms of density, okay? And the way we're going to do this is as follows. We know, right, that the small parameter that's going to govern the validity of this hydrodynamic approximation is that we're looking on big scales compared to the mean free path, okay? So we need to make sure that whatever expression for the current we find has this, we need it to be an expansion in this small parameter, okay, of mean free path divided by sort of length scale. Now, if we think about how we might sort of access this typical length scale of fluctuations, that's captured by the spatial derivative, right, when we act on a function. So what we conclude is that if we want to write down an expression for the current, we should do so using as few derivatives as we can. And the fewest derivatives we can use is just one. So we could write something like this. Here, d is just a constant called the diffusion constant. Maybe I can go ahead and write this in this way for shorthand. And here it is, right? This is my sort of minimal hydrodynamic theory for how electrons will move in a metal in the absence of Coulomb, like long-range Coulomb interactions that we're not going to worry about today. Okay. And this is essentially the theory of ohmic transport. If we ask how this diffusion equation will be modified in the presence of an external electric field, what you find is that this equation just needs to be modified to pick up a factor of electrical conductivity times electric field. And this conductivity is just going to be our diffusion constant times a thermodynamic susceptibility. This is just our Einstein relation. Okay. So this is sort of the simplest hydrodynamics, and I think it gives you kind of a flavor for how one approaches these sort of complicated, chaotic many-body systems sort of with a hydrodynamic perspective. Okay. All right. So this is not what people typically have in mind when they say hydrodynamic electron fluid. So what people really have in mind when they talk about hydrodynamic electron fluids is systems that have electrons that obey sort of Navier-Stokes equations, or things that are approximately like Navier-Stokes equations, which are a little more complicated than this simple diffusion equation. And so the way we get to the Navier-Stokes equations is quite simple. We just need to add another conservation law to hydrodynamics. Then we go from the diffusion equation to our sort of classic gas and liquid fluid equations from textbooks. So what we do is we imagine if we wanted to get to our Navier-Stokes equations, we say that we need essentially charge or mass conservation. So that's going to sort of at least abstractly look the same as before. We'll have a continuity equation. But then we also want to add a second conserved quantity, which is going to be momentum. Okay. So abstractly, I'll write the momentum density as pi subscript I. And there's also going to be a current of momentum. This is a 2-index object called tau for stress tensor. Okay. And just like before, hydrodynamics is going to consist of me giving you an expression for J and tau in terms of my densities of conserved quantities n and pi. Okay. Now, before we do that, let's sort of briefly mention why this is not typically the case in an electron fluid in a metal, right? So on the previous slide, we had this picture where the electrons are moving around in this impurity dominated landscape. And every time an electron hits one of those impurities, it's going to dump its momentum into the ionic lattice. And that ionic lattice, if we had a truly infinite solid, it would just absorb that momentum into a phonon, a lattice vibration. But in the lab, it can often be the case that momentum is very quickly relaxed, into the clamps that hold your device together. So usually when the electrons are scattering off of this lattice, effectively that momentum is gone. That's not always the case, but it often is. Okay. And since in many metals, either due to impurities or phonon scattering, electrons do frequently scatter off of the lattice, it's often the case in ordinary metals that momentum is not conserved. Okay. But sometimes, you might have, for example, in graphene, a metal where you have a very small Fermi surface relative. So here's our sort of Brillouin zone, okay? And here's maybe our Fermi surface, this little sort of small pocket here. In graphene, you'd have two, but that's not really important. We can just consider one of them. So because this Fermi surface is so small, right? If the electrons are scattering off of each other, they're really not going to be able to sort of jump all the way across the Brillouin zone. They're not going to be able to Umklapp momentum away. And so when you have a small Fermi surface like in graphene, you might hope to have approximate momentum conservation. Okay. All right. So when you have approximate momentum conservation, the hydrodynamic equations that you write down in the textbook fluid follow from the assumption of a symmetry called Galilean symmetry. And this just gives you one what we call constitutive relation for J and tau in terms of our conserved quantities. And they'll look something like this. So the charge current will be proportional to momentum density. And the stress tensor will have two terms. There will be a pressure. This is within linear response. So I could even say this is like dp dn times delta n delta ji. And then there's a tensor called the viscosity tensor, dk of pi l, something like this. And this viscosity tensor turns out for the Galilean fluid to have a single component called the shear viscosity. Just quickly put some indices on it, but they're not super important. Okay. So these are the ordinary textbook fluid equations. This is, I would say, the modern way that we would think about where these equations come from. It doesn't rely on any microscopic derivation. These come from symmetry principles. Okay. And so as long as we don't have, a lot of momentum conservation, we might think that they would apply to a typical electron fluid as well. With a small Fermi surface. I'll come back to that point a little later, but at least for graphene, this turns out to be a reasonable assumption. Okay. So now that we maybe have some appreciation for how hydrodynamics might arise in an electronic system, let's try to understand how we could look for it. Okay. Oh, so I got a direct message about even in a small Fermi surface, don't you have momentum relaxation from impurities? So, okay, in terms of impurities, that's still definitely true. So in addition to having a small Fermi surface, let me just go back quickly. We also need to have a low impurity density and not have strong momentum relaxing phonon scattering, et cetera. But the point to make is just that in systems like graphene, this is achievable, okay? So we can really find a system that has a small Fermi surface and it doesn't have a lot of impurity scattering, so we can hope to see this hydrodynamic behavior. Okay, so let's now think about what's a simple experiment we could do to try and look for this effect. Actually, this was first thought of by the Soviet physicist Gurdjieff all the way back in 1963. He was thinking about semiconductors at the time, not graphene, but the same principle holds. And what he proposed was that you should just carve a sort of narrow channel of width W. And depending on essentially the dominant kind of scattering in the system, he pointed out that you would see sort of 3 different qualitative behaviors for, let's say the conductance of this device. Okay, so in particular, we're going to look at how the conductance of this device scales with the width. Okay. All right. So conductance, just as a quick reminder, right, is 1 over our resistance from freshman E&M. Okay. So if we have impurity dominated transport, so this is going to be our sort of ohmic regime. In this regime, you should think of there's so many different impurities that as the electrons sort of move through the channel, they're just scattering off of impurities. And in this, and not really the walls. And in this case, what's going to happen is that you can think of each kind of patch of this channel as being like a little local resistor, just build a resistor network for this channel, combining nearest neighbors and so on. And in that case, this conductance, just by the, whatever it's called, parallel resistors law, will scale linearly with the width. Okay, so the resistance is going down because we've got a lot of resistors in parallel. That means the conductance goes up and it's proportional to W. Okay. All right. Now, more generally, we could write that the conductance should scale as W times the time scale that it takes us to relax momentum. So I'll just say momentum relaxing time scale. In the impurity case, that's just the time to get from one impurity to the next, and it's constant. It's not scaling with the system size. So that's why we have G scaling with W. Now, one scenario you could imagine is that you just removed all the impurities and you had a single electron, or non-interacting electrons moving down the channel. And in this case, the electrons would just bounce back and forth between the walls. This is a transport regime called ballistic transport. And in this regime, this momentum relaxing time scale is linear in W because, well, there's a transit time to get from one wall to the next. So you could estimate that the conductance of this device will scale as W squared. Okay. And then finally, if we have viscous hydrodynamics, so we've got a lot of collisions between electrons, but they're all momentum conserving. Okay, and we can only relax momentum when we collide at the walls. Okay, so I'll sort of schematically denote that as momentum conserving collisions in the middle. Momentum relaxing collisions at the boundary. Well, in this case, you can sort of estimate tau by saying, how long will it take for an electron to essentially make it from one boundary to the other? And if it has to random walk from one boundary to the next, because there's all these momentum conserving collisions in the middle, well, we're going to have our random walk scaling of the time it takes to travel a distance W scaling as W squared. So we predict in the presence of viscous hydrodynamics that this conductance should scale as W cubed. If you solve the Navier-Stokes equations, you'll get to this same result. And you'll find that the prefactor here is viscosity eta. And this viscosity eta is scaling with the collision time for our electron-electron momentum conserving collisions, which would be 1 over temperature squared. So this is quite a striking prediction, right? Even, these are going to be good conductors. They're going to have a low absolute or high absolute conductance, low resistance. And yet we're going to have this insulating temperature dependence where as you cool the system down, the conductance goes down, okay? I've seen it defined before that the definition of a metal is basically whether resistance increases or decreases with temperature. And so if you use that definition, this would be a good conductor that's also an insulator, just to emphasize that this is kind of a surprising effect, especially without any Kondo physics or anything like that. Okay. So as I mentioned, this is a very old experimental prediction, but it took a very, very long time to sort of really convincingly see this. And it's just because the material quality in 1963 was not very good, at least compared to today. Okay, so I think this is the best demonstration of the Guernsey effect. So I'll try not to sort of give a history lesson and just sort of focus on what we know today. So this is an experiment that was done in graphene, and they did something a little bit different, similar in spirit, but different in practice, and I think a little better in practice. So they basically took their channel and they cut this, or rather, yeah, they sort of etch in this kind of constriction. So it's going to force all of the flow in the channel to sort of go through this choke point. Okay. And the reason this is a little bit better is that we were a little lazy on the last slide about the boundary conditions and how electrons scatter off of the boundary. This is something we don't understand in a microscopic metal, and it does actually change the scaling that you predict if you get unlucky. So I think the idea with this constriction is very sensible, that it's going to be a little less sensitive to boundary conditions, because the sort of most interesting boundary condition is the one that you have to flow through the constriction. Nevertheless, you can still hope to see some of the signatures that Gurji predicted. In particular, this temperature scaling of conductance and the fact that the conductance will increase or resistance will go down as a function of temperature. And that's this data that's shown right here. So this solid line here, this is the ballistic resistance of this device. You can actually calculate it from first principles, and the experiment agrees well with that prediction. And as you heat the system up, right, you see that before around 130 Kelvin or so, the conductance is decreasing as a function of, or increasing as a function of temperature. Resistance is decreasing. So this is our viscous Gurji effect, okay, right here. All right. Now, just as sort of a follow-up on this experiment, and partly, you know, just to sort of try out some new technologies, but also to better understand this hydrodynamic regime in the first place, we can try to sort of dig a little deeper into this kind of constriction flow. So, you know, hydrodynamics, when we often think about it, we don't just think about things like conductance through a pipe. You know, we think about spatial patterns of vorticity and current profiles. And so we might ask, you know, can you really visualize hydrodynamics in this way? Can you actually see sort of the local onset of hydrodynamics by looking at how current flows through devices in non-trivial ways? Now, of course, this is not so easy for these for graphene, because the length scales are very small. However, we can, in principle, sort of, you know, at least imagine what would happen if we were able to visualize how current flows through the same device. So this is the same experiment, or same device at any rate. We've got a slit that we're pushing current through, and let's ask how current would flow through such a device. So firstly, in this left panel, we have our sort of ohmic ordinary boring transport case. Okay, so this is the classic transport theory. Ohm's law is obeyed locally, and in this case, what happens is you see that as you try to push this current through a constriction, you can see that the current will all bunch up right near the edges. This is actually something called the lightning rod effect. It's very aptly named because this is how lightning rods work. So if you have a lightning rod, right, the goal is to seed essentially lightning strike at that point, basically so that it doesn't strike, you know, your house or the flammable part of the house. And so how lightning rods work is that they have very sharp corners, okay? And if you solve the Laplace equation, just, you know, from undergrad E&M, but you solve it around a sharp corner, you find that the electric fields blow up right as you approach that corner, okay? And that blow up is the same thing that you're seeing here, okay? Ohm's equation ohmic transport means Laplace's equation is obeyed for the local potential, and so the current blow up at this edge is the same physics responsible for lightning rods. Okay, that's kind of fun. Now in the second panel, we have ballistic transport. So here we're imagining that there's just no interactions at all, no impurities, no electron scattering. And in this case, oh, and sorry, in the second panel, right, we're looking at sort of the absolute value of the current, how it flows through the channel as we pass through a sort of spatial cross section of the constriction. So we have the peaks here, right? Okay. In the ballistic case, we see that the current profile is approximately flat. And this we can also reason through. If you have ballistic transport, a particle will basically either make it through the constriction or it won't, right? So if we have the constriction here and we have a particle that just happens to hit the constriction, it's just gone. It's bounced back. We're never seeing it again. The only particles that make it through are the ones that happen to just, straight shoot through the first time. And there's no reason why they should prefer to move through the center of the device versus the sides. And so up to sort of small boundary effects coming from the finite thickness of the constriction, you expect a completely flat current profile. And then lastly, if you look in the viscous regime, sort of amusingly, the current will bunch itself up at the center of the device. Okay. This is almost, I've heard Lebedev explain this by saying that, the current, the particles that sort of sit near the edges of the constriction sort of slow down and they kind of shield the particles in the middle from the wall. And so the dominant flow will sort of be through the middle of the constriction. Okay, it's maybe a colloquium description, but I think it's okay. The summary that I want to give is that, not only does the Gurgey effect, if you like, or not only does hydrodynamics tell us that the conductance of this object will change depending on which regime you're in, but there are also sort of striking patterns of current flow that, if hydrodynamics is correct, we should be able to visualize. Okay. So the way we do this in an experiment is using a technique called nitrogen vacancy center magnetometry. And basically, this just means that we have a little diamond sitting at the edge of a metallic tip, and there's a NV center, basically a quantum spin in that diamond. That's a very sensitive magnetic field detector. Okay, and we basically just invert the Biot-Savart law that we all know, and we have a two-dimensional current profile. So this J is kind of like it exists locally in the plane. And it turns out that we only need to measure one component of the magnetic field, and that's enough, together with current conservation, to actually reconstruct the whole current profile in the plane. Okay. So by just scanning this NV center over the device as we run a current through, we can actually image how current is flowing locally. And the resolution of this device is limited by this sort of sample tip distance, which in the experiment that we did was, on the order of 100 nanometers. We can probably do better in the future, but this is what we have at the moment. Okay. So just as a warm-up, we can ask what happens at room temperature. So at room temperature, we expect that electron-phonon scattering dominates, and this electron-phonon scattering happens to be momentum relaxing. Okay. It often is, and it's no different in graphene. So we expect to see very ohmic transport, and indeed that's the case. We can see our sort of double peaked current profile, quite striking in our experimental data. And although, this device is quite large compared to our spatial resolution, it turns out that spatial resolution actually sort of smears the image out quite a bit. So this is a sort of comparison of the smeared sort of current profile to this is what you see in experiment, and this is what we believe the actual current profile looked like. So it's far, far sharper than what you can image, but that's just life. Okay. So now that we sort of have our ohmic transport at room temperature, which is what we expect, we can now cool this system down to 128 Kelvin. This is where we believe hydrodynamics is existing based on this this earlier work done by Andre Geim. So in these two plots, we're looking at finite density graphene. So at finite density, we've got a small Fermi surface, but still a Fermi surface nonetheless. And so we expect that this sort of textbook hydrodynamics is going to be appropriate. Okay. And sure enough, we see that as you cool the system down, you can see your sort of two ohmic peaks in the current profile through the center of this constriction go away, and you get this sort of single peaked profile. Now, when you take into account the smearing, it's sort of difficult to pinpoint what your actual scattering rates are. So I'm not going to tell you that we can image the viscosity of graphene. That's a little bit aggressive. But if we do look for the sort of best fit to our data, we do find something consistent with prior experiments. Rather than quoting to you a viscosity, I'll just tell you the relevant scattering lengths. So the electron-electron scattering length in graphene at 128 Kelvin, according to our estimates, is about 500 nanometers. That's compatible actually with the earlier constriction experiment that I showed you. You can try to back out this length scale from their resistivity, and they get a similar number. And our momentum relaxing or impurity or phonon scattering rates, these are on the order of 3 to 4 microns. Okay, and so we can sort of compare this image to simulations of the Boltzmann equation on this Fermi surface, and this is the best fit of the Boltzmann equation to our data. Okay.
Andrew, sorry to interrupt you. May I ask which group, which experimental group did this work?
This is Anya Jayek's group at UCSB.
Oh, okay.
Yeah, I should briefly mention, although I don't have time to sort of discuss, but there were 2 other imaging experiments that were posted a few months before ours. We sort of spent a bit longer analyzing our data, but yeah, there's also the I'm forgetting, Elani's group, I think, at Weitzman, and then Jacobi at Harvard have also done similar experiments. Elani uses a slightly different technique, but it's the same principle of local imaging. Okay.
We have interrupted you already. Another question. I'm Walter. So in the previous slide, you showed that if you have ballistic regime, it's just flat, but this peak looks pretty flat to me in the middle. How do you know it's not ballistic?
So, okay, that's a good question. I mean, this is part of the challenge of analyzing this data. Actually, if you believe that we know the device geometry, you can rule out fairly convincingly that this is not flat enough. So if I go back here, you can see that you still have kind of flat current even in the viscous case, but it sort of starts to slope down, reasonably towards the edges. Whereas in the ballistic case, if I sort of undo my drawing, it's really flat, quite close to the edge. And these numerically, you can distinguish. They're a little subtle. It's not as easy as distinguishing from the ohmic case, but you can tell them apart if you're confident in all of your data points. Now, in practice, we are not quite so confident in our data points, so that's why in this sort of error plot we have this huge window of. It kind of looks like, I can find a different color. This is kind of the regime where we think we're most likely to be. This is where the darkest purples are. And you can see that it does extend into the ballistic regime. So we can't rule it out systematically.
Just a follow-up to Walter's question at this moment. Why don't you change the constriction width? Because you have a dependence there between ballistic and
well, we should have. I was not. I didn't. Yeah. We should have in retrospect. I mean, this was the first time that these techniques were applied to hydrodynamics, and then so it's just in retrospect we should have done things a little differently. But yeah, it's also just one of the challenges I should also mention in fairness is that in practice, to do these experiments, they're both time intensive to do the imaging, but also you've got to make the sample, and you'll go through many samples that are not good. Like if you have an impurity that happens to be close to this constriction. So graphene has the Coulomb impurities, they're pretty sparse, but if you have one near the constriction, it's just going to ruin the whole image because you're going to see that impurity sort of warps the current profile. And so to yeah, to pattern a sort of complex device many, many times over until you can sort of, you get lucky with where your impurities are. That's not an easy experimental task. You know, in the future, we'll probably be better with it, but that's sort of one reason why it wasn't done the first time. All right. Okay, since in the interest of time, let me move on because there's a sort of second story I'd like to say a little bit about. So thus far, I've talked about graphene, and I think that we're pretty confident that graphene probably is viscous. I think if you sort of combine multiple experiments together, a very consistent story begins to be told. Maybe you don't believe sort of any one experiment on its own, but when you put a picture together, you have got a lot of circumstantial evidence. Okay. Now, I think what's actually sort of more exciting in this field in some regards are proposals that hydrodynamic phenomena can be seen in a slew of more complicated materials. Palladium cobaltate is actually one of the simpler of a whole zoo of materials that are coming out where experimentalists say they have evidence for hydrodynamics. Okay, palladium cobaltate is a member of a family of materials called delaphossites, and they all have approximately two-dimensional Fermi surfaces. The crystal is three-dimensional, but if you just look at the Fermi surface computed in some sort of semi-first principles model here, it's pretty much a flat cylinder. There's a little bit of bending, but not too much in the third dimension. It's not a small Fermi surface, right? Like Umklapp a priori is not negligible on this Fermi surface, but let's sort of sweep that under the rug for the moment. Okay, the key thing I'd like to emphasize about this Fermi surface is that it might seem kind of 2D, like graphene's Fermi surface, but there's one important difference, which is that it has a hexagon-shaped Fermi surface, and the circle and the hexagon are two different shapes, as we learn in kindergarten. Okay, I'm being a little bit flippant about that point, but part of the reason for this is that until recently, people really didn't take this very seriously. So in 2015, there was an experiment done by Philip Moll and Andy McKenzie, and they looked for evidence of the Gurgey effect in this material. Let me explain sort of a little bit what this plot is showing. So rho over rho naught. For some reason, I don't understand, experimentalists like to talk about the resistivity of a channel, even though this answer is fundamentally geometry dependent. So this is basically equal to the resistance of the device times W. Okay, so what do you expect to see? If you have ballistic transport, you would see that this is going to scale as 1 over W. If you have ohmic transport, this quantity is just going to be a number like 1, constant. And if you have viscous transport, this would be 1 over W quantity squared. So if you plot this rho versus 1 over W, you expect to see basically a straight line for ballistic transport and something that curves up if you have viscous transport. And so, okay, you can see that these authors have sort of tried to say that these data points curve up. Usually when I give this talk, people complain to me about this, so I'm going to say up front, you know, I was not on this paper. I agree that this is a very weak signal, but this was reported and it is what it is, okay? So there was a belief that maybe palladium cobaltate was at the onset of hydrodynamic flow. Okay. I mean, this is certainly not deep in a viscous regime, but the idea was that the sign was at least more consistent with viscous flow than with ohmic behavior. So that was the idea. Okay. Now, these blue and red lines are theory lines, and the theory that they had at the time, these experimentalists had, is a theory of an isotropic Fermi surface, of electrons on an isotropic Fermi surface with momentum conserving and momentum relaxing scattering. And you know, they ran the simulation and they backed out some estimates for LEE and so on. But from our perspective as theorists, you know, this is maybe a little bit unsettling because, as I mentioned, the circle and the hexagon are two different shapes. And it's worth checking, how much does hydrodynamics depend on the shape of the Fermi surface? So, okay, just to sort of quickly explain the answer here, we went through and calculated this both from sort of phenomenological arguments and in kinetic theory models with hexagonal Fermi surfaces. And you find that your Navier-Stokes equations from before are modified in two ways. So the first thing that happens is that your charge current, in addition to having this sort of momentum density dependent piece, it now picks up a new term, which looks kind of like what you would have had in ohmic transport. This might seem kind of stupid and boring, like who cares and why not just write this before? But it turns out this is kind of a curious thing. You may have heard this called incoherent diffusion in recent years by like Sean Hartnell and friends. It's essentially coming from the fact that once you break the isotropy of the Fermi surface, it's possible to find current, you can make a current flow without momentum, okay? So current and momentum are no longer the same, and this gives you a new term in hydrodynamics. I've argued that this will strongly affect plasmon decay, although I'm told that is not an easy experiment to do. But in principle, if you can do it, there are very striking signatures for this. Okay, what's a little more exciting is our stress tensor. So just to cut to the chase, so we had a stress tensor before that had this 4-component viscosity tensor. And what happens in this hexagonal Fermi surface is that you get the same isotropic terms that we had before, plus one more piece. And the last piece is sort of a curious object. So this epsilon here is Levi-Civita tensor, so it's antisymmetric object like this. And we call this term rotational viscosity. Okay? So there's a new kind of viscosity that can arise with a hexagonal Fermi surface that has never been seen before in experiment, I would argue. And this is sort of something genuinely new about hydrodynamics that you can have in an electronic setting, okay, in a material like palladium cobaltate. So let me explain a little bit about why this can happen. So ordinarily, okay, in an electron or in a fluid, if you have rotational invariance, okay, angular momentum has to be conserved. But it turns out that angular momentum, because it, okay, for technical reasons, it's a little different than other conserved quantities. It doesn't give you a new propagating conserved density. It rather constrains the hydrodynamic equations you already have. And the constraint that angular momentum conservation gives you is that the stress tensor be symmetric. Now, once we talk about electrons on a Fermi surface, in an ionic lattice where rotational symmetry is broken so strongly that the Fermi surface is, a hexagon, we don't have angular momentum conservation anymore. It's not even approximate, right? As you move electrons around the Fermi surface, they can torque onto the lattice and back. And if you tried to create vorticity, this would sort of amount to trying to twist the Fermi surface. And that's going to cost you energy, right? Because the lattice has picked out its preferred orientation of the hexagon. So this is basically the microscopic origin of this new kind of viscosity. And just as a quick comparison point, the reason we don't talk about rotational elasticity is that in solids, the symmetry, the rotational symmetry group that was continuous sort of microscopically spontaneously breaks to some discrete subgroup. And the fact that the breaking is spontaneous actually changes sort of the way that you would write down the theory of elasticity. So this is why this is sort of a unique effect for this electron fluid. You wouldn't see it in elastic solids. Okay. Another effect that I'd like to quickly mention that was not really appreciated in 2015 is that the Guergy effect itself is very sensitive to geometry in general metals. So in this example, let's say we've got a hexagon Fermi surface. It turns out that if you look at the conductance of this channel, here we're dividing it by width squared. So all these numbers are just ballistic limits, okay? Okay. as you sort of heat the system up, just think of this axis as like temperature squared. Okay. If we have no momentum relaxation at sort of large temperature, this is our viscous regime, where G is scaling like W cubed, or on this plot, we have a linear function. However, you can see that sometimes we're claiming that you can actually have this very non-monotonic dependence on temperature as you cool down. And the origin of this in a nutshell is that imagine that your Fermi surface happened to be very effectively aligned with the channel. Now, particles on a Fermi surface always travel, with a group velocity that is perpendicular to the Fermi surface. So if this Fermi surface is aligned with the channel, you've got a big fraction of particles that just moves parallel to the channel walls. So in the ballistic regime, they can't scatter off of the walls, and they will lead to a huge conductance. And that's, in a nutshell, why the conductance can spike up when the channel happens to be closely aligned. So here on this blue curve, you have alignment. On the purple curve, you're sort of not aligned. The reason I bring this up is that this tells you that you've got to be very careful when you look for things like the Gurgey effect in this material. You have to be very careful with how your crystal is patterned, how the experiment was done, et cetera. Yeah. All right. So these are some theoretical predictions. And after we had these theoretical predictions, we went and asked Andy McKenzie for his experimental data. And they graciously gave us data. And so we've replotted it, and now I'll sort of give you my interpretation of that experiment. So now that we maybe have a little bit of a better eye for what to look for, the first thing that we're going to do is we're going to replot G over W squared as a function of temperature. And what you're seeing in this plot is right, there's no viscous rise as a function of temperature. The conductance is strictly decreasing. Okay. So there's no evidence for a viscous regime here. And if we ask, well, where was this old evidence for a viscous regime coming from? It's actually coming from the fact that these curves are a bit out of order. So what are we doing here? The purple line is the smallest channel, the red line is the biggest channel, and the rainbow sort of fills in between, going from small to big. But if you look at these sort of highest curves, right, this is not the rainbow. We've got like green, teals and purples and blues all out of sync. And it turns out that this is responsible for this kind of funny data that they were plotting that seemed to give evidence for the Gurgey effect. But this signature exists all the way down to quote unquote 0 temperature. Okay. So they could measure down to like 2 Kelvin and this effect is still there at 2 Kelvin. This material has a Fermi temperature in the thousands, so we don't think that scattering is very strong at 2 Kelvin. Okay, so that's a little disconcerting. It turns out that if you sort of normalize this data by the 0 temperature value, then with a single fitting parameter that essentially amounts to how strongly ballistic particles scatter at the walls, we can actually fit all of the temperature dependence of this data for all 5 of the small channel devices using the bulk resistivity that we glean from the very big channel. So we can actually quantitatively explain this data without any viscosity at all. So we don't think that this material, after all of our work to try and understand anisotropic hydrodynamics, we don't think this material is actually hydrodynamic. Although there may be other anisotropic materials where our theory is relevant, and we hope someone finds one. There are 2 quick papers that showed up in the past 2 months that I'd like to sort of mention as sort of follow-ups to this discussion. So the first one is another paper that I wrote with Caleb, where we describe how you can actually detect rotational viscosity. To summarize, it's a very non-trivial thing to do for technical reasons. It turns out that rotational and shear viscosity will always kind of come together, so you'll only be able to measure their sum. But we believe that the simplest experiment you can do to find rotational viscosity is basically to study heating patterns in this 8-terminal device. And this 8-terminal device allows you to sort of look at patterns of flow that have different symmetry, and you can actually extract all the different viscosities in your system by sort of changing which currents sources or which leads are sort of sources versus sinks. So, okay, there's a reference here. If you're interested, you can read more about it. The other quick thing is there was an experiment, I think, showing up last week that has seen this very directed ballistic transport that I was explaining a couple of minutes ago. So this is on a logarithmic scale. So the effect is like factors of 2 or 3. So depending on how you orient this palladium cobaltate Fermi surface relative to your channel, you can get very different conductance. And so I think that this may in part have been responsible for some of this data that they were showing being a little wonky, that even if these devices were cut, just a couple degrees off, that might explain all of that data that they were showing. And they, at the time, they didn't realize this would be a substantial thing to worry about. So anyway, sort of fun ballistic physics in palladium cobaltate, though not hydrodynamic. Anyway, here are some sort of take-home messages and open questions that I'll just leave up. And I'm happy to answer some questions. Thanks.
Okay, thank you very much for the interesting talk. Yeah, now it's 1:45. I think we can have a few minutes of question.
So I have a question.
Yeah, go ahead.
So is it possible to do a pump probe measurement where you have an optical pump and measure the probe in terms of conductivity, like current, so that you essentially create a temperature, like 2 temperatures for electrons and phonons, and then you can see the effect of temperature on the electrons over time. That way you can maybe screen the temperature dependence of the hydrodynamic behavior.
I mean, it's possible. I guess I'm reminded of, there were similar experiments along those lines on graphene that did try to sort of back out different scattering rates back in like 2013, but the timescales involved are quite fast, especially relative to hydrodynamic timescales. So like the timescales to set up a viscous flow pattern might be very slow compared to some of the timescales involved, especially if you heat up the phonons quite a lot. They'll eventually heat the electrons up. So yeah, it might be possible, but it's probably sort of subtle. I mean, there definitely would be very interesting experiments to do if you can sort of optically pump and sort of try to source flows, at a finite frequency. This may be a nice new way of distinguishing viscous and ballistic transport. That's largely unexplored, I would say, even theoretically.
Another quick question: the optical properties, does the viscous versus ballistic transport have an effect on the optical properties, say the surface plasma polarity on resonance, stuff like that?
Okay, so at finite wave number, it can in principle. I'm not sure about plasmon polarity. There's like a couple papers on this, but I don't know them very well, and so I don't know if there's a particularly striking signal. The most striking thing I think about plasmons, so plasmons basically, in the hydrodynamic language, I would say that the plasmon is what the sound wave of a fluid becomes when you turn on long-range Coulomb interactions. And so in the hydrodynamic regime, the sort of viscous attenuation constant for sound will become the attenuation constant for plasmons. So, so to some degree, like hydrodynamics should play a role in that, but it may be very hard to see.
Okay.
Yeah.
Water.
So going back to your discussion of anisotropy with this hexagonal surface, I was wondering if the masses have intrinsic anisotropy because of the band structure, which is often more the case for holes than for electrons. How would that come in? Could you have envision like a viscous Hall transport, and where maybe there are additional interesting things coming from the intrinsic anisotropies of the mass in a crystal.
Okay, so I think there are sort of two things here that I'd like to address separately. So firstly, in terms of like electrons versus holes, or having both electrons and holes, that's all going to be built into this same framework as long as you can have some kind of electron hole scattering mechanism. If you have like decoupled electron hole fluids, then you need to write down two fluid equations. But in principle, if they scatter, you'll just have one set of equations. So that's sort of not too big of a deal. As for mass anisotropy, indeed, that could be quite substantial, and that can probably change many features of these equations. For the hexagonal Fermi surface, what happens is that I think the solid state physicists say that the symmetry group is D6, and that is actually quite a big group. I mean, it may not feel that way, but it's actually very big, and it means that most kinds of anisotropies you could try to write down are symmetry forbidden. So in this discussion, I've assumed that you have D6 symmetry on the Fermi surface, and that blocks, for example, any additional anisotropy you could try to write down in eta. It blocks the pressure having like different XX versus XYY components. That's kind of like a mass anisotropy effect, I think. Yeah, if you have a rectangular Fermi surface, then probably you can have crazy things like pressures that are not isotropic and so on. That would be interesting to study.
Thank you. Very nice talk.
Harvey.
Hey, very nice talk, by the way. Thank you for that. And so I just had a couple of questions. The first one was, there was another recent experiment on graphene where they measured like a non-local resistance. And essentially they showed that if you have a viscous flow, you can have a negative non-local resistance. I was just wondering if you'd come across that and what your take on that was. And
yeah, I mean, that was actually, that experiment was done before this constriction flow. And look, it's a nice experiment, but the only caveat to that is that ballistic effects can also give you a negative signal. And so you have to look at the temperature dependence of the effect to sort of distinguish between ballistic and viscous. I think that's why this constriction is a little better, because it's sort of easier to see the breakdown of ballistic physics.
Okay, so that still doesn't allow you to distinguish between the hydrodynamic and the ballistic regime.
Right.
Okay. And secondly, also, like when you built the models for the different current profiles for like viscous and ballistic regimes, like the one which Walter was pointing out about earlier, is the viscosity there just like a free parameter, or do you derive that from like first principle somehow?
So, okay, in hydrodynamics, things like this rotational viscosity and shear viscosity, these are phenomenological parameters, and they need to be calculated microscopically. So you can do that using kinetic theory, for example. And yeah, I mean, I don't, there's nothing like super striking in those calculations, I would say. Like rotational viscosity is probably going to be a little smaller than shear viscosity, but not like thousands of times smaller. So, yeah.
Oh, Harsh.
Yeah, so sorry, this is a slightly crazy question. Is there any possibility of getting into a nonlinear regime where one might see kind of turbulent flows?
It's not a crazy question. A lot of people have asked it. I'm actually very pessimistic on this front compared to most people in the field. The reason is, there's a couple of reasons. Firstly, turbulence in 2 dimensions is quite different from turbulence in 3 dimensions, and large scale structure is sort of what is easiest to see. But large scale structure is where momentum relaxing physics sort of wins. And so I think for that reason, turbulence will be very hard to find in graphene. People have looked for it, and like, I don't know, like there were people, I think at some March meeting said they had some weird signature that they thought might be turbulent, but I've never seen a paper sort of actually come out on it. So I expect that it's indeed quite a delicate subject.
Okay. Oh, Shuray.
Hi, Andy, nice talk. So you've been studying the longitudinal transport, the viscosity, hydrodynamics. So how about the transverse direction, the transverse Hall conductivity? So signatures in the Hall, signatures of hydrodynamics in the transverse Hall conductivity, and if you apply magnetic field, usually the Hall conductivity in a strong magnetic field associated with the topological quantities. So anything like that?
So yeah, so there's a non-negligible literature on that I didn't discuss. If you look up like hydrodynamic Hall viscosity in electrons, there's a number of papers. Also in my review, like there's some citations. There's been recent experiments sort of after that review was written that have seen Hall viscosity in graphene, but yeah, I mean, that's sort of a starting point.
So this has been seen experimentally, the Hall viscosity?
Yeah, I wouldn't say it's they haven't seen something topological, but they have seen Hall viscosity. It's like a semi-classical Hall viscosity, and that's been observed.
Thanks.
Yeah, remember there's a recent paper, maybe in Science. Yeah. Any other questions? Well, we have had quite a few good questions and nice discussions. I think we can let's thank Andrew again for giving us a very interesting talk. Thank you, Andrew.
You're welcome.
So Andrew will stay after talk. He will stay a little bit longer for further discussion. If you guys want, you can stay.